5 minutes? Sponsored by Induction. Today we're going to look at sequences of partial products of factors of the form 1 plus a sub n and partial sums of terms of the form a sub n, where a sub n is always non-negative. Let's start by looking at the sequence 1 over n. We're going to look at the partial products. I'm going to show you that the partial products diverge. The mth partial product is always m plus 1. I'm going to prove this using induction. For the base case, I have to show that p1 is 1 plus 1. Well, what's p1? It's just the first factor and nothing else. The first factor is 1 plus 1, and that is 2. So this is obviously a true statement. Next, the induction step. We can notice that if we look at the m plus 1th partial sum, that is basically the same as the mth partial sum times the next factor. And since we already assumed for induction that pm is m plus 1, we're going to put that here. And we can do some algebra simplifying. We're going to get m plus 1 plus 1. That's exactly what we wanted to show. Great. Now, let's look at the sequence 1 over n squared. And I computed these lovely little things for the partial products. 2, 2.5, 2.78, 2.95. Wow, that's a lot better than m plus 1. I'm going to bet this actually converges. Great. And I am going to prove that the sequence of partial products converges if and only if the sequence of partial sums converges. So let's look at some properties of these sequences. I'm going to prove to you that Sm is at least 0 and Pm is at least 1 always, and both of these are monotone. So we're going to prove this using induction, and we're going to make use of the fact that any an is non-negative. So the base case, I'm going to show that S1 is at least 0 and P1 is at least 1. Well, S1 is just A1 and P1 is at least 1 plus A1, so these, oh my god, it's obvious. But now, the induction step. We're going to assume these, and we're going to look at the next partial sum, add the next term, and this is positive, so it's at least this, okay? And the next partial product, well, Pm is positive, and 1 plus a positive number is at least 1, so if you multiply a positive number by a number at least 1, it's at least that number. So that proves the induction, and next we just have to show that they're both monotone. Come on, I made that argument already. You're adding a non-negative number, so it's at least this, and you're multiplying by a number by at least 1, so it's at least that. So it's increasing. Look at this. We have our monotone sequences that are constantly increasing. A bound on them would restrict their growth, meaning they have to settle on some value and thus converge. Let's bound them. I am going to bound Pm under e to the Sm. So it's a known result that 1 plus x is less than or equal to e to the x. We're going to use this fact. We're going to use induction again. So first of all, the base case. P1 is the first factor. S1 is the first term. 1 plus something is less than or equal to e to the something. Well, that's the known fact that we have. So this is a true statement. So next, the induction step. We're going to look at the next partial product. So we're going to take out Pm. And now we're going to look at this product, and we're going to see these are both positive numbers. And what is greater than or equal to Pm? Well, e to the Sm. And what is greater than or equal to 1 plus something? E to the something. So we're going to take this, replace it with this is at least, and this is at least. So this is valid because they're positive numbers, and we're going to add the exponent. Wow. And what we get when we add the exponents? The next partial sum. Oh my goodness. So that's the induction done. But now we're going to bound Sm underneath Pm, always. So induction. Wow, I'm sure you know it by now. S1 is less than P1. Oh my god, come on. It's plus 1. Whatever. Next, the induction step. We're going to assume this and look at the next partial sum. And we are assuming that Pm is greater than Sm, so we can replace it with this. And we already know that Pm is at least 1. So if we multiply this by Pm, it's going to be at least as big. So we can make that inequality again. And what do we have? The next partial product. Oh my gosh. That's what we wanted to show. Hey, Daniel. Yeah. In conclusion, we know that both of these are bounded below and monotone. If in addition we know that Pm converges, then it must be bounded. And because of this, we know that that upper bound for Pm must also be an upper bound for Sm. So Sm is monotone and bounded and therefore convergent. But on the other hand, if we know that Sm converges, we know it is bounded, meaning e to the Sm is bounded. And this here gives an upper bound for Pm from that. So Pm is monotone and bounded, and thus it is convergent. We've proved it both ways. Hallelujah! Products converges? No, damn it. Subscribe to Induction today. Get it for only 2.7182.